great pleasure to have Jason Macron from Ballard Space Center from UCL here today. So we have been interacting with Jason for quite a number of years, but finally it's a great pleasure to have him here. So he's a professor of astrostatistics and astrophysics at the astroinformatics at the University College London, and he's also a Turing Fellow at the Alan Turing Institute. His research interests are more on the side of astronomy, but very much of application of Bayesian statistics, Bayesian techniques, and machine learning and AI into the astrophysics and astrostatistics side of the spectrum. He's also founder of the company called Kaganova, which is a startup focusing on developing geometric AI techniques for metaverse, which is a new buzzword around us. So here today, he'll be talking to us about the geometric deep learning on the sphere. Just to update you all, this talk will be recorded up until the point of questions, and the question and answer session will not be recorded. So if you are not really agreeing to the privacy policy, anything here, you could quit the seminar, but it's not massive deal here, I take. And if you can mute your microphones and if you can sort of turn off the videos, it might please stop the distractions. Thank you again, Jason, over to you.
Thanks very much, Jayden. Great, okay, so yes, so I'm going to talk to you today about some work we've been doing on geometric deep learning, in particular geometric deep learning on the sphere, which comes up a lot in cosmology and astrophysics as we look out over the night sky, the celestial sphere. We observe data on the sphere, and also in computer graphics and virtual reality as well. So I'll talk kind of generally to start with, and then I'll focus on a couple of works, a couple of papers we've had published at ICLR on this topic, which is in collaboration with a number of people listed here. So I'm basically going to start by talking more generally about kind of connections between physics and deep learning, and I think there's a lot each can learn from the other, really. So I'll start kind of very general, then talk a bit about spherical CNNs, why we need specifically spherical or geometric deep learning on manifolds. And then I'll focus on our two recent papers on trying to extend these types of techniques and make them computationally scalable. So before we get going, I've got a brief kind of Mentimeter survey. I'm going to just switch my screen sharing now. So if you go to this link, I see a few people have gone there already and started filling it in, but I'll just share the results, and I've got a couple more questions to put to you as well. So hopefully you can now see my other screen sharing. I'll assume you can. Someone shout if you can't. So yeah, I've put this question to you. What factors were responsible for the deep learning revolution? Feel free to put, many terms in and add more than once. But yeah, we can see we've got quite a few things through already. Things like data, big data, algorithms, GPU, compute, some kind of specific, there's been a lot of advances in kind of NLP, and I guess, CNNs, algorithms, they were kind of getting at the idea of architectures. So there are a lot of factors here, but I think there's one factor that actually people often forget about. It's not on the top of people's minds. And actually, I think that's something to do with this connection between physics and deep learning, and how the architectures of many deep learning models and CNNs in particular encapture properties of symmetry that we know the natural world exhibits, which is one of the reasons they're so effective. So I've got a next question for you now, which will link to some other concepts in the talk. So firstly, very quickly, have people heard of concepts of conservation of energy and conservation of momentum? These are, what generally one thinks about as the fundamental, some fundamental laws of physics. And so, these are pretty common terms. It seems, most people have, well, everyone really has heard of these. So let me move on to the next question, which is, have you heard of a notion of equivariance in deep learning models? This is a property of some deep learning models. It's also helped me for this talk to see like how much detail I go into these topics as different parts of the talk. Yeah, so some people maybe heard a little bit, but not a lot, and would like to know more. And then some people have not heard of these concepts, and there's some who are very familiar. So basically, through this talk, I'm going to actually draw connections between these principles of energy conservation and conservation of momentum, and kind of equivariance properties. And we'll see how these things are actually quite linked through this principle of symmetry. And this, really goes to these deep connections between physics and deep learning. So let me switch back to my slides now. All right, again, I'm going to assume you can see the right screen now, but shout if you can't. So let me start by talking generally about these ideas of symmetry and deep learning and connections to physics. We often approach problems in different ways from the physics perspective or a deep learning perspective. With physics, we're generally modeling ideas from first principles, whereas with deep learning in particular, we're really trying to learn informative representations of data or structure in data. But we're trying to generally address the same type of questions. We're trying to understand the world, and often by trying to develop generative models or trying to do inference. So there's a lot of similarities in what we're trying to do, but actually differences in the way we go about it between physics approach and deep learning approach. And both of these are very difficult. And so there's a lot I think each area can learn from the other, and we can really try and work hand in hand to address these difficult problems. So in this talk, I'm really going to be focusing on general ideas from physics and how these can be, and often are, integrated in deep learning models at these kind of levels of these kind of principled levels rather than maybe specifics. But in many cases, we're doing the reverse. We're seeing how deep learning can help us address problems in physics, and lots of other work of ours, we're targeting this approach. But generally, I think it's great if we can try and explore both of these, how each area can help and inform the other. And as I alluded to in those questions at the beginning, actually, I think this is one of the key factors that drove the deep learning revolution that is maybe not so apparent as things like data and compute. So it's often said that physics is nothing more than the study of symmetry. Steven Weinberg, a Nobel laureate, who unfortunately passed away last year, was a big kind of icon in physics, basically said symmetry is really the key to nature's secrets. And he won the Nobel Prize for unification of the electromagnetic and the weak nuclear force. And the way he did that was by essentially exploring the symmetry of the physics. So symmetry is absolutely key in physics. Let's probe that word symmetry a bit more and see what we actually mean by symmetry. Normally in kind of everyday life, we think of symmetry as some kind of transformation of an object or something like that. So here we've got a photo of some mountains reflected in a lake. And if we flip the photo upside down, it's similar to the original photo. So we've got some kind of, in this case, approximate mirror symmetry. But mirror symmetry is something we're all familiar with from looking in the mirror. We're also quite familiar with ideas of rotational symmetry, where here we have a playing card and we pick it up and rotate it around. And if we rotate it the right amount and put it back down, then it looks the same. So in this setting, we're talking about symmetries of objects under some transformation. In physics, we usually think of symmetries in a slightly different way. So we're typically considering continuous symmetries, so some kind of continuous transformation of a system, and it's symmetric in the sense that it's invariant under that transformation. So if we have some kind of closed physical system and we translate it spatially, so say we drop a ball in one area of the room and then go to another area of the room and drop a ball, the laws of physics are the same in both those settings. So the system is invariant to a spatial translation. The laws of physics don't change with where you are. Another very common symmetry is rotational symmetry. As we rotate a system, if its laws of physics or of motion, for example, don't change, then it can have rotational symmetry. And another very common type of symmetry we have in physics is time translational symmetry. So, for a closed system, so ignoring any external factors, if I drop a ball now and then I do it again 1 minute later, it's going to behave in the same way. So the laws of physics don't change in time. So these are very kind of fundamental and common symmetries that we find in throughout physics. And actually these kind of symmetries were connected to the conservation laws in physics by a woman called Emmy Noether, who was a prominent mathematician at around the early 1900s. And she proved that for every continuous symmetry, there is a conserved quantity, and in fact, also the reverse. So these ideas that are familiar to us, these ideas of conservation of momentum or angular momentum or of energy, they're actually not necessarily the underlying fundamental laws. They actually derive from these symmetries of the systems that we experience. So translational symmetry leads us to conservation of momentum, for example. So we can see here, symmetry is really at the heart of physics. And it's the foundation of, what we often think is these fundamental laws. Right, well, how does this link and connect to deep learning? With deep learning, we really want to, we have these deep learning models that can learn arbitrary complex functions, but we typically need to give them a helping hand. We induce some inductive bias into these models so they can do a better job at representing the types of models we're likely to have in practice. So what we want to do is encode these notions of symmetry into deep learning models, such that we can capture this kind of fundamental properties of the data or of the natural world that we'll be looking at. So I would argue that actually this is one of the key factors that led to this deep learning revolutions, with CNNs basically resulting in a step change in performance and classification accuracy in the kind of early 2010s. It was, yes, the factors we discussed earlier, increasing compute and availability of data, but a key factor is this CNN architecture that basically captured these translational symmetries of images of the natural world that they were applied to. So I think, this was kind of, one of the key factors that has really led to this deep learning revolution, is this notion of encoding symmetry and encoding kind of these underlying physical understanding of the world in our deep learning models. So let me just try and formalize that a bit more. How do CNNs capture these translational symmetries? And it's through a concept called translational equivariance. So let me just discuss what that is. So formally, this is written by the maths here, but really it's just saying that if we're considering some kind of operator, so it might be constructing a feature map in a neural network, for example. So it could be a convolutional layer. So basically transforming the signal. So in this case, let's think of a translation. Whether we do that before or after the operator to construct the feature map, we get the same result. So this is this notion of equivariance. And if the transformation's a translation, then it's translational equivariance. So we can draw this kind of commutative diagram here where we've got X, we make some feature map, we'll do some transformation A to get Y, and then do some transformation or translation. If we do that in the reverse order, we get the same thing. So this is what is termed equivariance. So if we think of this graphically, here we've got an image, we can compute some kind of feature map, and then we can translate it. So here we've translated it up and to the right. So you can see the cat's eye is moved up. It's exactly the same as doing the translation first and then computing the feature map. And this basically means that our representation space in our deep learning model is well behaved and has some nice properties, and means that we can effectively learn in that space. So basically what we're doing here is we're imposing what's called some inductive bias into the deep learning model. So some properties of the data or the natural world that we're observing, in this case, equivariance to symmetry transformations. And this then allows our model to be learned in a much more principled and effective manner. In some sense, we're capturing this some physical understanding of our generative process in the model. So in some sense, so slightly hand wavy, but in some sense, you can think of this as being the fact that we only need to learn a pattern in images once, and it doesn't really matter where they are. So here we've got a picture of a cat's face in the center there. We want our model to be able to learn that, but on the right, it's still a cat, and we don't want to have to learn that all over again, just that because the cat's in a different part of the image. So in a sense, we want to learn these properties once and not have to learn them over and over again, depending on wherever they may happen to be. So yeah, that's kind of the general comments I wanted to make about these connections between physics, symmetry, and deep learning. Now I'll get a bit more specific and talk about some of these problems where we have spherical data and exactly how we encoded symmetry in standard like planar CNNs. We want to encode the symmetries of the sphere in spherical CNN so we can be effective for this type of data. So, I mean, firstly, data on the sphere is actually everywhere. It's maybe not quite in the popular consciousness so much, but if you look closely, actually, you can find spherical data in all sorts of settings. And so what we really need to do now is encode those properties, those symmetries of the sphere and kind of rotations, which are the extension of translations in the planar setting, into our models. So, I mean, there's the obvious cases where you've got spherical data. If you're looking at the Earth, and you're looking down on the Earth, you know, that's very well approximated by a sphere. You've got data over the surface of a sphere. In astrophysics, we look out over the night sky, observe data on the celestial sphere. But actually, in many applications, you find you have spherical data. For example, in medical imaging, if we look at diffusion magnetic resonance imaging, where we're trying to essentially image the white matter fibers in the brain, you actually end up with a spherical deconvolution problem in each voxel. So you're really trying to determine what directions does water diffuse in the brain to trace these white matter fibers. So obviously the brain is not a sphere, but if you look at the problem you're studying is about signals over directions, and then you do have spherical data. So you get spherical data in all sorts of applications. And basically we need now deep learning models so that we can extend the, you know, as I'm sure everyone knows extremely well, AI has been remarkably successful in dealing with and making predictions and processing standard images. We'd like to be able to do the same types of things for spherical data, but we can't just use the existing techniques to do that. So I think, as I more or less have said already, you know, whenever we observe over directions or look out over angles, we get spherical data. And two areas I'm quite interested in is studying the cosmic microwave background in cosmology, where we've got spherical images. So that's looking very far out and very way back in time to the early universe. But similarly, in computer graphics and virtual reality, if we have a light field, we're looking at incident light over all directions, we get a spherical image. So again, we have spherical 360 data. So we've got a lot of this data. We want to do deep learning with it. Why don't we just pick up the deep learning techniques we've got already and apply them? So we could take these standard techniques, Euclidean deep learning techniques. We could take our spherical data, and in some sense, we could unroll it or project it to a plane, and then we could apply our planar deep learning techniques. The problem with that is it's just not effective for various reasons. One reason is, well, there's a distortion involved in doing this projection. If you take the Earth and do this projection, on the right, you'll see Greenland looks almost the same size as Africa. But actually, if you look on the left, when you're viewing it on the sphere, Greenland's about 10 times smaller than Africa. So we get distortions that depend on, you know, where on the sphere we are or where relative to how the projection is done. So we introduce distortions, and we basically break the symmetries and the geometric properties of the sphere. So in that previous slide, I showed you one projection. Well, you might argue, well, don't use that projection, use a different projection. So yes, there are a whole host of different types of projections that can be considered, and they have you know, different pros and cons, but actually it's well known that there's no possible projection of the sphere that can preserve both shapes and areas. So it's completely unavoidable to have distortions. So we can't really get very far just by doing projections. And yeah, one other point to note is that, you know, we on the sphere, we want to have this rotational equivariance, because rotations are the kind of analog of translations. But certainly that wouldn't be captured if we just picked up existing standard Euclidean deep learning models. So another approach is you can make a graph representation of your data. And this is a huge area of geometric deep learning with graph-based approaches. And this is very powerful and very flexible framework. So in many cases, this is a great approach. But with flexibility, you do lose something. If we really know we're on the sphere or on a particular manifold, that information is not captured in a graph representation. So you can approximate that setting, but you lose that knowledge of the underlying manifold that you're on. And actually, this also results in breaking the continuous symmetries and geometric properties of the sphere. And so this means actually you can't exactly capture these ideas of, or these notions of rotational equivariance. What we need to do is define and construct deep learning techniques natively on the sphere. So as I said, the analog of translations is rotations. So we need to be able to do rotations on the sphere, and we want our deep learning models, our CNNs here, to exhibit rotational equivariance. Just as we saw, that was one of the properties of planar CNNs that made them so effective. The problem is the sphere is actually a much more challenging setting than the kind of Euclidean space when we're dealing with, say, 2D images. On the sphere, it's actually well known that there's no discretization of the sphere or no pixelization of the sphere that's invariant to rotation. So what that means is if you start with a pixelization of the sphere, you rotate it, and then you lay these two pixelizations, these two sets of samples on top of each other, the sample positions don't align. And I've just picked one sampling scheme here, but again, this is a known property of the sphere. There doesn't exist a sampling scheme that has this property. When you rotate the pixels, they'll never align for all possible rotations. And this is very different to the Euclidean setting. If we start with an image, we can translate it and the pixels will line up. That's not a problem. So this means that actually we cannot strictly capture these equivariance properties in a discretized setting because there is no, in a sense, kind of perfect discretization of the sphere. So what we do to avoid this is we consider a Fourier approach. So basically we develop our deep learning models in the Fourier space of the sphere, which is called spherical harmonic representation. And just like on a line, if you have a periodic signal, you get a discrete Fourier space. Well, here, because of the fact that we're on the sphere, and it's a bounded manifold, we actually end up with a continuous Fourier space. So we end up with a discrete Fourier space of the continuous signal. So that means in a discrete set of samples of Fourier coefficients, we can capture the underlying continuous symmetries and properties of the sphere. And so that's how we can access these kind of rotational equivariance properties. So spherical CNNs doing this have been constructed, basically developing convolutions on the sphere, pointwise nonlinear activations on functions on the sphere, and combining these as usual. For example, a convolution followed by a ReLU or some other nonlinear activation function. So these have been developed and worked by Cohen and Estevez. And basically, we know how to rotate signals on the sphere. We can do this effectively. Again, we can actually do this in harmonic space to avoid pixelization artifacts. We can also convolve signals on the sphere. And really, the spherical setting here is, again, just the analog of the Euclidean setting. We have a filter or a kernel, and we basically put it down at all different positions, so all different rotations row here, multiply it by the signal, and then sum it up or integrate. So we've got these notions of rotation and convolution on the sphere. Again, we can compute the convolution in harmonic space to avoid pixelization artifacts. So as I said, we can do this computation in the Fourier space. And so now we can get a rotationally equivariant operator. We can do a convolution followed by rotation. It's just the same as doing the rotation first and then the convolution. So we have these nice rotational equivariance properties for the convolution operator. The other thing we need with spherical CNNs or CNNs in general is some nonlinearity. This is usually introduced through a pointwise activation function. Because this is acting pointwise in the Euclidean setting, this is translationally equivariant because all those pixels line up if you shift them over, and you're just applying these nonlinear activations pointwise. You know, if you apply the activation, then shift things, it's the same as shifting things and then applying the activation. So you have this equivariance. This, unfortunately, is not the case in the spherical setting because, as we showed before, if you rotate spherical samples or pixels, they don't line up. And so this actually is going to break the equivariance properties. So actually, we've done some numerical tests here at floating point precision. We see that here we look at the equivariance errors for different types of convolutions. I kind of won't go into the specifics of exactly what these are, but they're basically to floating point precision here, which is the precision we use, we get machine precision accuracy. But for the ReLU and nonlinear activation functions, accuracy is at the level of about 30, 34, 37%. So, you know, we do have equivariance to some degree, but it's, but, you know, there's still a reasonable error there. Nevertheless, these are the approaches developed by Cohen and Estevez. They don't have perfect equivariance, but they have reasonable equivariance. And actually, these models have been found to perform very well and essentially doing spherical convolutions or directional convolutions that lead you to what's called SO3, the rotation group, followed by activations. So this is the kind of the first techniques to do spherical CNNs, and yeah, as I said, they perform generally well. So let me now come to some of our work in this space, building on top of these prior works, and also, as we'll come to a bit later, you know, a key factor here is how we can scale these techniques. They're, you know, computationally demanding, and we want to be able to apply them to real, you know, real world high resolution data. So yeah, so I'm gonna not go into too much detail here, but try and just give you a bit of a flavor of like the approach we take here, and basically, you know, and also approaches taken by others on which we build, is that really, you know, as I've said throughout, symmetry is the key property here. And so we need, you know, the kind of mathematical structure to deal with symmetry, and that's group theory. So basically, these kind of techniques are essentially built on a group theoretic construction. And actually, there's a, you know, again, because we're dealing with rotations now, we want these rotational equivariance properties. The mathematical machinery that we use is actually the same as the type of machinery that's used for studying angular momenta in quantum mechanics. So yeah, I mean, obviously the application domain is very different. You know, we're not studying quantum mechanics, but the kind of mathematical tools and machinery that we use here, again, has this kind of deep connection. A lot of these techniques were actually developed for quantum mechanics. So again, here there's, you know, deep interplay between physics and deep learning, and how we can kind of leverage this mathematical toolkit, if you like. So I'm not really going to go into the details of these techniques, but basically just to say, you know, so we've constructed this generalized spherical CNN framework that's also efficient. We basically have three different types of layers in a block, if you like. We have a linear layer, a non-linear layer, and then another linear layer. So it's a bit different to your typical, where it's usually like a linear followed by a non-linear. And then these linear layers are essentially types of spherical convolutions. And the non-linear layers are some types of spherical activation functions. You know, we could make use of the ReLUs like we saw before. They don't have the best equivariance properties, but it's not too bad. But we also consider other types of non-linearities, and that's where the connection to the kind of machinery of quantum mechanics comes in, really. So we really build on these other influential works of, you know, I spoke about the works of Cohen and Estevez already. Condor proposed this tensor product type activation function, which is an activation function computed in the harmonic space of the sphere. And so by constructing that in a certain way, one's able to perfectly capture these rotational equivariance properties. So, you know, we basically advocate kind of a hybrid approach where we can use all of these different types of layers together, but they're also extremely computationally costly, especially all these computations based in the Fourier space. And so we also introduced a number of variants to basically improve the efficiency. Basically introducing some other concepts from standard machine learning models like channel-wise structure, also constrained generalized convolutions, and then also optimizing what are called the degree mixing set in these tensor product activation functions. And then finally, we need to be able to work in Fourier space, actually have both the sphere and the rotation group. So also leveraging some previous work in this space on efficient sampling theory and efficient transforms. So that's, gives you hopefully a flavor of the kind of contributions of this work. I'm not really going to go into details of these, but you're welcome to ask me more about them later if you like, or you can see further details in the paper. So with this approach, we have a big reduction both in the computational cost and the memory requirements. So in these settings where we get really strict rotational equivariance to machine precision, even for the activation functions, that's also what Condor et al. Are able to achieve. But we get orders of magnitude reduction in computational cost and 30 times so reduction in memory. But this is still relatively small band limit. So this is the spherical harmonic band limit. So in terms of number of pixels, that's basically like the band limit squared, more or less, or a factor of 2. So we're talking about 30,000 pixels or so. So still very low resolution spherical images. And in the final part of my talk in a minute, I'll come to how we can scale this to high dimensional data. So these techniques are efficient. We've got a big improvement over the prior state of the art, but still they struggle to scale to really high resolution data. And we'll see how we can adapt them to do that in a minute. We also studied the equivariance properties of these basically tensor product activations and our generalized convolutions, and find indeed the equivariance errors are basically 0 to machine precision. So let me just show you a few kind of benchmark problems where we've applied these techniques. Like I said, I'm not really going to go in depth in the applications here, but I'll show you a few applications for these works, and then a few more applications later. The canonical problem, even on the sphere, is studying MNIST digits. It's not a very realistic setting, but nevertheless, it's a very well controlled setting. So this has been considered in numerous papers. So we also consider this problem so we can compare to others. And basically the MNIST digits are projected onto the sphere, and then we want to try and classify them. And we consider two settings where the digits are not rotated, so as on the left, or where they're rotated. When they're not rotated, actually you're not too far away from a standard planar deep learning problem if your digits are always in the center. So planar techniques work reasonably well. But as soon as you start introducing rotations, that's no longer the case. So we construct a kind of hybrid architecture like I was advocating previously, including a variety of different types of spherical convolutions, convolutions on the rotation group, and these kind of generalized convolutions with tensor product activation functions. These, as I said, these kind of tensor product activations are quite computationally costly. So what we generally do, as people traditionally do with CNNs, is reduce the resolution and kind of increase the number of channels as we go through these layers deeper into the network. So here's the results of these experiments. So we have these two settings. So NR is non-rotate and R is rotate. And here we consider both training and test. So NR means we train where the digits aren't rotated, and then on the test set, we also don't rotate them. And then we see how well we can do in classification. As I said, this is not too dissimilar to a planar setting. So actually planar CNNs work very well here. But now let's consider the case. So yeah, I've got planar CNNs, a variety of other approaches, and then our approaches with some variance. The second one is just is a little more computationally efficient. But yeah, they're somewhat similar. So in the next setting, we consider where we rotate our digits when we're training, and we also rotate when we're testing. Planar CNNs don't do too poorly, because actually what we're doing here is we're actually using augmentation to learn the fact that we're on the sphere. And so planar CNNs can do okay here. We get 90% accuracy. But you'll see the spherical approaches do better than that. And we can go a step further because we can encode this equivariance to rotations. In fact, we can make it perfectly, the model perfectly invariant to rotations. We can actually train where digits are always at the center, but then when we test, the digits can be anywhere. But because we're not sensitive to rotations or where they are, we should be able to handle that no problem. And indeed, if we try this with planar CNNs, they fail miserably. There's 10 digits. We're not doing much better than random with just 11% classification accuracy. Whereas the spherical techniques are, are all doing very well. And, I think they're all doing very well. We marginally provide the state of the art here, but it's, they're all doing very well, basically. But let me come on to some slightly more more realistic examples. Like I said, spherical data comes up in lots of settings. Another kind of common canonical benchmark problem is 3D shape classification. So you might have a number of 3D models and you want to be able to automatically classify them. So again, you wouldn't naively think of this as spherical data. You've got a complex mesh. But actually, you can form a number of projections of that mesh onto a sphere. And what is key in this setting is, you don't want to be sensitive to what direction the model is facing. So you really want to have this invariance to rotations. So, that's where the spherical CNNs can be very powerful. So again, we consider this type of shape retrieval problem, not only classifying, but finding similar shapes. I'm not going to go through these different metrics, but there's a variety of metrics that are considered on this problem. And yeah, the spherical methods are generally working very well here. I think we get the state of the art in 4 of the 6 metrics. Another problem we've considered is predicting the atomization energy of molecules. So again, you can have a spherical model basically of each atom making up the model. The molecule. And basically here, again, we try and predict the total energy to basically atomize the molecule. And we compared this to previous spherical CNN approaches, so Cohen and Condor. So this is the RMS error in this benchmark problem. And actually also to the state of the art for this problem, which actually there are techniques, older techniques that have done very well for this particular type of problem. And we find actually we improve over these techniques quite considerably, and also with a much more efficient representation. So just a quick flavor of a few different types of spherical problems that we've considered, common benchmark problems, so we can compare with these other techniques. So in the final part of the talk, I want to talk about how we can extend these techniques to high resolution data, typical of more practical applications, for example, in cosmology, virtual reality, and elsewhere. As I said, these techniques that we've developed are efficient. We've really optimized their computational nature, but they're still very costly, and we can't scale them to high resolution data. So to do this, we've introduced ideas of scattering networks on the sphere. So yeah, basically what I said, with these previous approaches, we can't scale them, but we do have these rotational equivariance properties. So what we want to do is have the best of both worlds. We want to keep this rotational equivariance, but we also want to be able to scale the techniques to high resolution data. So we basically embrace the kind of hybrid approach that we promoted in our previous work of Cobb et al. And basically suggest using lots of different spherical layers together so that you can leverage their different properties alongside each other. And so what we want to do is introduce a new type of layer in this framework. And this new layer should have a number of properties. Firstly, it should be scalable, so we can compute it with high resolution data. We're actually considering this as the first layer in the model. So what we really, as I said before, as is typical with CNNs, you reduce the resolution as you go deeper into the network. And so what we want to do is we want this first layer to really to be able to mix the information from high frequencies down to low frequencies, such that subsequent layers have access to that high frequency information. So this is a key property we need. We want to keep these rotational equivariance properties. That also means that, results in very good performance. So we want to keep that. And also we need a kind of effective representational space. So we need kind of stability and local invariance properties. I'll discuss in a bit more what I mean by that. So these are our kind of aims. These are the properties we need. And actually it turns out that scattering networks are a way to get all of these properties. So again, we've had a recent paper on this, which has just been accepted for ICLR and is coming out. Well, it's on the archive already, but it's going to be published in ICLR in May. So scattering networks scattering networks in general are based on wavelets essentially. So they've got a lot of similarities with convolutional neural nets, but we don't learn filter kernels. We use designed filter kernels that have some very nice mathematical properties. So to construct scattering networks on the sphere, we need wavelets on the sphere. We've also done a lot of work in the past in this area. So we adopt what are called scale discretized wavelets, where we have a wavelet now for a given J. And this plot on the right here shows in the spherical harmonic space for the different owls where the wavelet captures content from. And then we also have a scaling function that captures the low frequency information of our signal. So we've got wavelets, we've got scaling functions. Basically, the wavelet transform now is just the convolution of our signal with a wavelet at a given scale J. And we do this at a number of J's. So it's exactly the same convolution before, where we rotate the wavelet, project the signal onto that, basically. And we've done a lot of work actually in developing fast algorithms for wavelet transforms on the sphere. So we can scale these. Remember, that was one of the key properties we needed. So we're building these scattering networks on the sphere on top of wavelets, and the wavelets are scalable. So that means we can make scalable scattering representations. So the scattering transform on the sphere, basically scattering transforms were developed in a really quite seminal work by Mala back, I guess about 10 years ago now. So the extension of this to the sphere is really by direct analog of the Euclidean construction. So we can take the analog of each kind of component of it and put it together. There's a lot of deep mathematical theory behind this. I'm going to just cover this very generally. What we basically do is construct what we've called a scattering propagator. So it's basically we do a wavelet transform at a given scale, and we take the modulus or the absolute value. So in a sense, we've got a convolution with a filter, like a CNN. It's just in this case, that filter is a wavelet. And we've got a nonlinear activation. But instead of the traditional activations, like a ReLU or something else, we're using a modulus function here. And that's because it's non-expansive, and it actually means it preserves the stability properties of the wavelet representation. And this basically acts to mix signal content to low frequencies. So again, remember, that was property 2 that we wanted. We want this first layer to mix information to low frequencies such that other layers operating just at low resolution can capture that high frequency signal information. And then we can basically just cascade this and do it many times. Again, very much like a CNN where we cascade layers together. And then finally, there's another component of scattering transforms where we take this representation and we basically do some essentially averaging. We do some averaging of it, and that's performed by convolution with the scaling function. So that does a kind of low frequency averaging. So the scattering network now is basically just combining these things. So here's a tree showing our original image or signal F. We do a wavelet transform and we get these blue scaling coefficients and then the wavelets at this level. And then for each, we can go again. So we do another wavelet transform. We get scaling, wavelet coefficients, and we could just keep going indefinitely. Typically, we just consider 2 or 3 layers. But as I was saying before, there's a lot of similarity with CNNs here. We're doing convolutions with kernels. It's just we're using wavelets, and we have nonlinear activations. There's a slight difference here in that we also have this kind of low frequency averaging before we output our signals. So that's basically a scattering transform. Because it's based, we have scalable techniques to compute the wavelet transforms. We can also compute this efficiently. And because the wavelet transform is based on spherical convolutions that we showed earlier were rotationally equivariant, scattering networks are also rotationally equivariant. So now we've got this layer that we want that is computationally scalable, mixes information to low frequencies, is rotationally equivariant. The final property we need to test is that it's a good representational space. We don't want it to kind of mess up our signal representations. So what is a good representational space? Well, again, there's a number of kind of stability and invariance properties. So what we typically want is some kind of invariance to isometry. So an isometry would be like the translation or a rotation. So here we've got some examples of the digit 6, and they're rotated, so they're in slightly different positions. But in the representation space, they should all be in a kind of similar place. So we're not kind of messing up this information in the representation space. And that means that we can learn that effectively. So we want some isometric invariance. This is basically that written out formally. Again, I'm not really going to go into this in much detail, but what we basically say is the difference. So F is our signal, S is our scattering representation. And if we have some kind of isometry, some kind of transformation here, basically the change in the scattering representation is bounded. And that depends on the scale that we choose for this scattering network. So we've got these nice isometric invariance properties. We also want to be stable to diffeomorphisms, which you can think of really as just a distortion. So here we've got a few examples of sixes. They're all a bit different because people write sixes different. So there's small distortions you could think of mapping one to another. And in the representation space, in the scattering representation, again, we want these to be in a similar place. So we're not, messing this up. If we have a large distortion or diffeomorphism, so you could think of morphing a 6 into an 8, basically, again, we want that to go, if there's a large difference in the image space, we want a large difference in the representational space. So we want these 8s, which are kind of all similar, to be close to one another, but we want them to be distinct from where the 6s are. So again, this is basically having some kind of stability to diffeomorphisms. And again, we have some nice theorems to basically prove these kind of properties for the spherical scattering representation, but basically saying this difference in representation is bounded. So we're stable to small diffeomorphisms about an isometry, and also the size of this difference increases as the size of the diffeomorphism increases. So that's basically, diagrammatically, that's saying as this gets bigger, these points get further apart in the representation space. So basically we have a very well-behaved representation space, which means that we can do subsequent classification problems or whatever very effectively using that representation space. So we basically put these things together. We consider the scattering network as a first layer, prepending the architecture we had before with this. And now we address a number of problems. Just the properties. So just very briefly, we check the equivariance properties, and indeed equivariance errors are all very small. Typically we don't go below depth 2. So errors are typically on the level of 1% compared to the 30% error typical of a ReLU. So again, coming back to the MNIST problem, we now increase the resolution and we make the digits progressively smaller to make the problem more and more difficult. And we find that, if we attack this problem without the scattering representation, but just the architecture we had previously, that doesn't perform as well as if we introduce the scattering layer as well. So scattering here induces a significant improvement in classification accuracy. And then the final example I'll touch on, again, without going into a lot of detail, is classification of the cosmic microwave background. So we know from inflationary theory that the statistics of the CMB should be very close to a Gaussian random field on the sphere. But there are a number of alternative theories or variants of the theories that could give rise to non-Gaussianity in the CMB. So studying the properties of the CMB, whether it's Gaussian or not, can really tell us a lot about what's happening in the very early universe. So here we consider using simulations. We simulate Gaussian CMB and non-Gaussian CMB in some of these alternative models. the non-Gaussianity is very weak, so you can't really distinguish this by eye. But again, we can train a classification model for this, a spherical classification model. If we don't include scattering networks, we don't do much better than random. We're about 53% accurate. But if we include the scattering network as an initial layer, we can get up to 95% accuracy. So now we're able to scale up to these higher resolution settings with, here we've got 2 million pixels and apply these rotationally equivariant models. So that's basically all I wanted to say. Just to recap, I've hopefully highlighted the importance to you of encoding these kind of equivariance to symmetry transformations to encode some kind of physical understanding of the generative process. And this is a long history, this has been done for many, many years in CNNs, and it's one of the key reasons they're so effective. We really want to extend these kind of notions to deep learning techniques on manifolds, and so we need techniques constructed specifically on manifolds. I've been focusing here on the sphere because there's a lot of data in that setting, but these techniques also can be applied to other types of manifolds. And then I reviewed the general approaches to spherical CNNs that do provide rotational equivariance, and then some of our recent works to build on top of these really seminal papers of Cohen, Estevez, and Condor to provide more efficient approaches, and then also developing scattering networks to work together to really be able to scale to high resolution data such that we can now target more practical applications. So thanks very much for your attention. Very happy to answer any questions.
Okay, thank you, Jason. Thank you very much. It's absolutely stunning talk. Thank you.